Okay, math recap part 2. In this video we'll talk about gradient, divergence and curl. So let's start out with the gradient. Gradient operator is typically given by the del letter, or also known as nabla, and it is defined as in 3D as the basis vector in the first direction times the rate of change in that direction plus rate of change in the direction 2 plus rate of change in direction 3. So in index notation you would write this as EI d by dxi. Now this is obviously a vector, and if you operate your gradient operator on a scalar field, you get a vector as a result. And namely, say we operate on a field phi, then you write this as EI d phi dxi. So this is the gradient of the scalar field phi, which generally is a function of space and time. Now, as an example, to illustrate this, consider a hill, and here the constant value lines are typically called the contour lines. And if this wasn't a topographical field, but for example a pressure field or a temperature field, for pressure field these constant value lines would be the isobars, for temperature it would be the isotherms, etc. So these are contour lines. Now the gradient picks up the fastest rate of change, and so it is perpendicular to the contour lines. That is the direction of the gradient of phi at this point x. And so it's a vector because it has a direction and a magnitude. And the magnitude is how quickly your field phi is changing in this direction. And now if you want the rate of change in some arbitrary direction n, not the steepest, but some other direction n, then you find that d phi dn is the gradient of phi dotted with the n direction. So this is the gradient. Next we talk about divergence. In Cartesian form again, the divergence of a field is that of a vector field, so now we dot the gradient operator with a vector field. So this would be written as du1 by dx1 plus du2 by dx2. Again in index notation, dui dxi. So this is the divergence of a vector field, and it turns a vector into a scalar. Now you can also define the divergence on a second order tensor. So take the stress tensor that we've talked about, T, and let's consider the J component. So the J component of this divergence you obtain by dotting the divergence with the J basis vector, and you will write that as dt1j dx1 plus dt2j dx2 plus dt3j dx3. And in index notation you would write this as dtij dxi. And if t here is actually the stress tensor, then the divergence of the stress tensor gives you that force component in the j direction on a fluid element. So the divergence in this case turns a second order tensor into a vector. In summary, for the past two examples, the divergence lowers the order of your tensor by 1, whereas the gradient increases the order of the tensor by 1. Now, the third concept I wanted to discuss here is the curl. And the curl is the cross product of the gradient operator with a vector field. And so now let's consider again the jth component here. And you remember from the previous video that the cross product is can be written in index notation using the Levi-Civita symbol, and so it's epsilon ijk, and then it's duk dxj. So you can write this in matrix form as curl of u is the determinant of So I didn't write out all the components here, but you can fill these in yourselves. So the curl is a measure of how rotational a flow is, and a irrotational flow is defined to have zero curl. So grad cross u is 0. And this is in contrast to a zero divergence flow, where the divergence is 0. So this is a divergence free flow, also known as solenoidal.